How does the concept of time change near a black hole? Does time have a direction? How did Einstein describe the relationship between the past, present, and future? In this video, we'll explore these questions as we journey into the mysterious, mind-bending world of black holes and our understanding of time. Join us as we uncover the strange power these cosmic behemoths hold over space and time. We'll delve into what happens if you travel near a black hole, from the extreme physical effects on your body to the profound transformations in our perception of space-time and gravity. In principle, if you remain outside a black hole's event horizon, a threshold determined by its mass, you can actually approach the black hole's edge and then turn back. The size of a black hole can be estimated using a simple formula involving Newton's gravitational constant, g, the black hole's mass, m, and the speed of light, c. This calculation tells you how close you can get before you risk being pulled in. If you manage to hover near the brink and then return home, something remarkable happens. You will have traveled not just through space, but through time. Time passes more slowly at the edge of a black hole. Clocks farther away, say, back on Earth, will tick faster than yours. If you spend a year near a black hole, you might return to Earth to find that a decade, 1,000 years, or even 1 billion years have passed. What seems like a simple round trip through space is actually a voyage through time. When you return, you'll have journeyed into Earth's future. Einstein's theory of relativity revolutionized our understanding of space and time. It showed that time is not absolute or universal, but relative, depending on one's motion and the strength of nearby gravitational fields. Time is treated as a fourth dimension, woven together with the 3 dimensions of space. But the question of whether time has a built-in direction, an arrow that points from past to future, is still debated. Some physicists argue time flows from past to future because of how the universe began, the so-called arrow of time, while others suggest that time's arrow is just an illusion and that all moments, past, present, and future, exist equally. Einstein once poetically stated that the distinction between past, present, and future is only an illusion, however persistent. According to his perspective, every moment could be as real as every other, suggesting that time might not flow in one direction after all. Yet our everyday experience strongly suggests time does have a direction. We see eggs break but never spontaneously reassemble. People dive off boards into pools, but we never witness them leap backwards out of the water, defying gravity and logic. These observations reflect the arrow of time in our daily lives. What's startling is that the fundamental laws of physics actually treat the past and future symmetrically. There's nothing in these laws that forbids events from running backward. So the arrow of time we perceive must arise from something else, likely conditions set at the universe's birth. Near a black hole, these concepts of time become even more striking. The intense gravity of a black hole slows time drastically. If you could survive near its edge, a dangerous proposition, since the gravitational difference between your head and your feet could tear you apart, you'd witness some of the universe's most extreme phenomena. Time would crawl for you compared to distant observers. Clocks elsewhere would race ahead, making you, effectively, a time traveler into the future. Visualizing this requires a shift in perspective. Consider space-time diagrams from high school physics, where the vertical axis represents time, and the horizontal axis represents space. A beam of light emanating from a point fills out a cone, showing all possible directions in which it can travel. In the warped geometry near a black hole, space-time is so distorted that light cannot escape once it passes the event horizon. Not even light can outrun the black hole's immense gravitational pull, and so from the outside it appears as a region of eternal darkness. Some have imagined journeys to black holes, concepts that often appear in science fiction. While theoretically conceivable, the immense gravitational forces would create severe physical hardships. The analogy of paddling upstream in a waterfall helps illustrate this. Near a black hole's event horizon, space itself is thought to flow inward at the speed of light. And since nothing can outrun light, escape is impossible. If you approach a black hole, you're doomed to plunge in once you cross that horizon. If you could somehow endure the trip and return, a nearly impossible feat, you would find yourself far in the future of whatever world you left behind. This is not just speculation for the silver screen. Films like Interstellar have used this concept, inspired by scientific advisor and physicist Kip Thorne, to depict astronauts who experience only hours near a black hole while decades pass for their colleagues elsewhere. For now, all of this remains theoretical. We can't yet send people to black holes and bring them back to verify these predictions. Still, our growing understanding of black holes, gravity, and spacetime is opening new frontiers. We are learning that time is not fixed. It's a flexible dimension affected by speed, gravity, and the initial conditions of the cosmos. Who can say what future discoveries await as we continue to probe the depths of the universe? The study of black holes and the nature of time reminds us that we are still in the early stages of unraveling cosmic mysteries. Each step forward offers a fresh perspective on reality, challenging what we think we know and inspiring us to explore the unknown.